This is lecture number 6 entitled Mathematics in Computational Chemistry. There are actually 3 guiding questions that we talk about a little bit in this presentation. The first one is, what is the fundamental mathematical expression that needs to be solved in doing computational chemistry? What are the terms in this equation? What are their significance? And what variations can be used? We also talk about what are the approximations that can be used in doing computational chemistry. We'll talk a little bit about the pros and cons and a little bit about how the choice affects results in computing time. We'll talk more about those last 2 parts later in the course. And the third is we do a quick review of the fundamental units of measure that are used by computational chemists and how these units might be expressed. So let's go ahead and get started with fundamental mathematics. You probably have some familiarity with some models of atomic structures from your beginning chemistry class. The first one being the Bohr model. And that model basically suggests that electrons are billiard balls, or these little hard marbles, if you will, that rotate in a fixed orbit around a nucleus. So the nucleus is this large object. It has a positive charge. Electrons are negative, and they're very, very small as compared to the nucleus. And basically, these electrons rotate around the nucleus very much like the planet might rotate around the sun. Okay? And this model follows the rules of classical mechanics, where, again, as if you were trying to do a physics experiment on how billiard balls move, you would use that that's classical mechanics. That physics would help you predict how billiard balls are going to move on a pool table and what happens when they bang into another ball and that type of thing. That's classical mechanics. Okay. What Bohr did do in his model, which is it's been proved to be very wrong, as you'll see here momentarily, is he did introduce the concept of quantization, that being that these electrons have to have a very specific amount of energy. We find them in specific places in the atom or molecule, and that's the idea of quantization. Okay, the quantum model, we figured out, or it was figured out in the late 20s, early 30s, that the Bohr model didn't work very well. It was a pretty good model, but there were some real problems with it. So the quantum model came along, and basically this model said that electrons behave like waves. So they're not billiard balls, they're not these little hard marbles. They are waves. And so if you can imagine throwing a pebble into a pond or a lake, the rock would hit the lake, and then you'd see these little ripples move outward from where the rock hit. And that's the same idea here. You have these waves. And in a quantum model, we can only predict the probability of the location of an electron. So if you can imagine, if you were able to follow one molecule of water in the pond, as soon as you and you watch it, as soon as you think you know where that molecule of water is in a particular ripple, it has moved to some other place. So we really can't know where the molecule of water really is, but we can do a pretty good guess of where it might be at any given time. And the quantum model more accurately reflects the true nature of the atom. So here's, again, in the classical version, the electron follows a precise path, and that precise path is known as the quantum level. You probably remember the principal quantum number, n equals 1, 2, 3, 4, so on and so forth. And that principal quantum number describes the precise path of where the electron might be. So we can specify its position, its velocity at any given moment. We know a whole lot about the electron and where it is and where we can find it at any given time. Okay, so here's sort of a artist rendering of what this might look like. So that squiggly line there represents a precise path, and the little yellow dot there represents the electron. And so the electron has to stay on that path, and at any given time I can tell you where that electron might be. Okay. The quantum model, on the other hand, as I've said before, the classical model does not hold up. And the quantum model suggests that the electron's data can only be calculated as a probability. So I take that same path I just showed you a moment ago, and instead of a very precise line, you have now what's called an electron cloud. So if you can visualize that cloud there, what you need to understand is that there's an electron in there somewhere. We don't know exactly where the electron is, but it's in there somewhere. And all we can do is predict the probability that it might be on the far left-hand side or the far right-hand side, or it might be in the middle, or it might be on the top, or it might be on the bottom. We don't know exactly where it is, but it turns out that it's good enough to know about where the thing is. We know it's somewhere inside this electron cloud, and it turns out that if we know that, that's good enough to be able to do lots of really interesting things. Okay, the mathematics of computational chemistry, don't worry about the equation you're seeing there yet. We're going to get to it momentarily. Okay, but this equation is called the Schrodinger's equation. And this is the equation that lets us predict the probability of where that electron might be. And this particular type of equation is what's known as an eigenfunction. I'm not going to take time in the podcast to explain what an eigenfunction is. You should read about that in the chapter reading on mathematics and computational chemistry. But the Schrodinger equation that you see below, what you should notice there, well, let me go through some of this. H is something called a Hamiltonian operator. And you need to understand that in mathematics, an operator is something that does something to another number. So as a quick example, and again, you can read more about this in the chapter reading, the square root symbol or the square root function is an example of an operator. If I have the number 4 and I take the square root of 4, in other words, I do a square root operation on the number 4, I get some result. And if I take the square root of 4, my result is the number 2. So an operator is any mathematical process or method that does something to a number. So in this case, you have to be careful when you look at the Schrodinger equation. You see there H in front of that. I almost made a mistake myself. You have the H in front of that pitchfork-looking thing, and that is known as psi, or the wave function. You have to be careful not to read that as H times psi, okay, because it's not psi. It's not times. It is that H is doing something to that number called psi. Now, okay, what is that psi? That psi is the wave function. And if you go back one slide and look at that electron cloud, okay, we would call that the wave function. That electron cloud there is the wave function. So the wave function is a measure of where the electron might be. It's a measure of its probability. That's not quite true mathematically, but it's good enough for this lecture. So Schrodinger's equation, which you see in front of you, is the Hamiltonian doing something to this number called psi, or the wave function. And what we get out of that on the other side is the value E there, and E in this case represents the energy of the atom of the molecule. And then on the right-hand side, you notice we see psi again. And because of the fact that psi appears on both sides of that equation, okay, this mathematical equation is what's known as an eigenfunction. You cannot do algebra on Schrodinger's equation. You cannot say, oh, I have psi on both sides of the equal sign, therefore I simply cancel out psi. It's not that kind of mathematics. In eigenfunctions, you can't do simple algebra to cancel things out. So be careful about that. Lots of people look at this equation and they say, oh, H equals E. Well, no, that's not correct at all. Again, because this is an eigenfunction. And in the chapter reading, I give you some examples of what an eigenfunction is. I don't anticipate that you'll completely understand that, but you do have to understand that the mathematics here is not simple algebra. Okay, moving on, what we really want you to have some sense of is what is this Hamiltonian operator represented by the letter H. And there are a variety of forms of this. And what you see in front of you is an example of the Hamiltonian operator. And again, the chapter reading goes into each component of the Hamiltonian in great detail. Suffice it to say for this podcast that what we're looking at here, the first part there, the -1/2 times that E looking thing, that is the Greek symbol sigma, which means add all these things up. That first component there basically says what's the kinetic energy of the individual electrons in an atom or molecule. The next component, where you see the word elec and nuclei over the sigma signs. That's basically saying that part calculates the attractive force between the electrons and nuclei. You should understand that electrons are negative and nuclei are positive. And so that second term there with the two sigma signs says, okay, let's calculate how well or how much force there is or how much attractive force there is between the electrons and the nuclei. Going to the third term there where you see elec over top of the sigma signs, and you should be able to figure this out by now, that term there measures how much do the electrons repel each other. Okay, electrons don't like to be near each other. They're both electrical. They have negative charges, and so they want to repel. And the very last term on there where it has nuclei over top of the sigma signs, that term there says how well or how much do the nuclei in the molecules also repel each other. So basically the Hamiltonian calculates the repulsive and attractive forces of the electrons in the nuclei to each other, and it also calculates the kinetic energy of the electrons. The reason we put, by the way, a little superscript over there on the H is because we're only doing the Hamiltonian of the electrons, and you'll see a little bit about that momentarily. Okay, some of the approximations that we use in computational chemistry. There are three fundamental approximations that we use. And the first one is called Born-Oppenheimer, named after the scientist who created those. And the Born-Oppenheimer approximation says as following. As compared to electrons, nuclei are really, really large objects. They're huge as compared to an electron. And because they're so big, they move very slowly as compared to the electrons. The electrons move incredibly fast. Nuclei, comparatively, move very slow, and so because we have this huge difference between very, very fast moving electrons and very, very slow moving nuclei, what we do is we make the approximation that the nuclei don't move at all. We pretend it's incorrect, but we pretend in this approximation that the nuclei are fixed in space. They don't move. Wherever we put them, that's where they're going to stay, and that the electrons move around the nuclei relative to the nuclei, but the nuclei, wherever we put them, that's where they're going to stay, and they never ever move. That's not true. Obviously, nuclei do move in real atoms and real molecules, but to help simplify the mathematics and be able to run our calculation in a reasonable amount of time, we make the assumption or the approximation that the nuclei don't move. So that one should be pretty easy. The next one, the Hartree-Fock approximation, is a little bit harder, and I'm going to give you sort of the textbook definition of this. And the Hartree-Fock approximation says it's called the separation of many electron orbitals into a series of one electron orbitals. And I don't expect you to understand that, but that's how this approximation is defined. And we'll talk about that again momentarily. The third approximation is LCAO, or linear combination of atomic orbitals approximation. And basically we say molecular orbitals are formed from combining single atomic orbitals. And we'll give you a description of this momentarily. And sometimes in the literature, you will see that we refer to all three of these approximations as the Rotan-Hall equations. Okay, so you might encounter in your computational chemistry career in a textbook, in a journal article, somewhere, if they're talking about Rotan-Hall equations, they're referring to the Born-Oppenheimer, Hartree-Fock, and the LCAO approximations. These are the three basic approximations we use in computational chemistry. There are, needless to say, there are more of these, but these are the three basic ones, and these are the ones that we apply virtually all the time. So it's important that you know these. Okay, let's talk a little bit more about the Hartree-Fock approximation to give you a little better idea of what that's talking about. Okay, and if you can imagine, and there's a graphic there on the right, if you can imagine a series of 3 electrons, and I'm going to call them A, B, and C. Okay, each of these electrons has a negative charge, so I've represented each electron with a E and a minus sign on it, so you can see that each electron has a negative charge. And the question is, what does each electron see or feel? And you should be able to tell me the answer to that question, but I'll go ahead and tell it to you. Okay, each electron sees the repulsive force of the other electrons. So for example, electron A feels a repulsive force from electron B. They don't want to be close to each other, okay? So they feel a negative charge or a negative force between A and B. A also feels a repulsive force between A and C. B feels a force between B and C. So the arrows there say that each electron feels a repulsive force from each of the other two electrons. Well, it turns out that trying to calculate these things, if I try to do this, it's really, really hard to do. And I have to use calculus, and to solve this particular problem, I would need to use a calculus technique known as integration. I suspect many of you, because you're not in calculus, haven't come across integration yet. But basically, I would have to use a very complicated calculus mathematical formula called integration to calculate the total force between these three electrons. And it turns out that because I have three electrons, I have to use a multiple integral, so I have to not only integrate one time, but I've got to integrate multiple times, and the mathematics gets ugly very, very, very quickly. And if you accept the word that my claim that the mathematics for three electrons is really, really hard, imagine, if you will, you have a molecule that has hundreds of electrons in it. Each of the electrons sees each of the other electrons, and that's a real problem. Okay, so the problem is it's too hard to calculate when we have lots of electrons. Okay, if we try to do each electron seeing every other electron, your jobs are going to be running for days, weeks, months, years, decades, whatever the case may be. Okay, so here's the solution. Okay, let's pretend, and this is the approximation, let's pretend that one of the three electrons becomes one big electron. So you have to imagine this a little bit. Let's take electrons A and B and let's add them together. Okay, let's pretend they are not two small electrons, they are one big electron. So now we have a two electron system. We have electron AB, and imagine that as one electron, and then we have electron C. Well, what mathematics do I have to do now? I only have to do one calculation. I have to say, what force does electron C feel when it sees electron AB? Remember, AB is one big electron, okay? So I calculate that force between the lone electron and the large electron. So I calculate AB and what it feels or what it sees when it gets close to electron C. Once I've done that, okay, I switch the electrons. Now I'm going to take A and B apart, and I'm going to say A and C are now one big electron, okay? So A and C now see electron B. I calculate that energy or that force. Okay, I'm done with that. I take them apart. I take B and C. I add them together. They become electron BC, one big electron, and I calculate the force as compared to electron A. So if you can imagine hundreds of electrons, I have to do hundreds of mathematics that are taking a pair of electrons, pretending they are one electron, and comparing them to another single electron. And you can imagine even doing that approximation takes a really long time, which is why your jobs will sometimes take a long time to run. So that's the Hartree-Fock approximation. It's a really bad approximation. It really doesn't at all capture what's happening in the atoms or in the molecules, but it turns out it gives us a reasonable answer, and there are things we can do, and we'll talk about those later on, to improve on this approximation and make it a little bit better. Okay, LCAO, linear combination of atomic orbitals. Let me explain it in terms of what happens when you run a job. Okay, when you run a job, what you're doing is you're calculating a series of wave functions for every atom. So if you have the water molecule, you have an oxygen atom, you have a hydrogen atom, and you have a hydrogen atom. And what you're doing is you're solving Schrodinger's equation. You're solving the wave function for each atom. So you're basically saying, where are the electrons in the oxygen atom? Oh, I have an idea of where they are. Where are the electrons in each of the hydrogen atoms? Oh, I have an idea of where they are. So you calculate those wave functions. Okay? And the number of wave functions depends on your model chemistry. As you'll see next week and the following week, we'll do a lab, several labs actually, that help you figure out what are your wave functions, how many do you have, what do they look like, that type of thing. And that all comes from a discussion of basis sets, a term you've been exposed to so far. Okay? Every time you do, every calculation you do, or every wave function that you calculate is called an atomic orbital, or AO. And for every atom, you may have many, many, many atomic orbitals. It's not the case that you have one atomic orbital for each atom. Depending on your model chemistry, you'll have multiple atomic orbitals for a given atom. So, for example, depending on which basis set I choose, when I look at the oxygen atom in water, I may have 16, 17, 20, 40, 50, 90, 120 atomic orbitals for that single oxygen atom. Okay? And once I have calculated that, and again, that will depend, the number of wave functions, the number of atomic orbitals you have will depend on your basis set. I want to find the wave function for the entire molecule, and that wave function is going to be called the MO, or molecular orbital. And just like you're going to have more than one AO for each atom, you're going to have more than one molecular orbital for a given molecule, and we'll do a lab pretty soon related to that as well. Okay, but anyway, to find the MOs, what you do is you add up, or you do a linear combination. Linear combination is a fancy term for add them together. You add up all of the atomic orbitals. Okay, so you take all the atomic orbitals that have been calculated and you add them all up. The good news is that the computer does all of this for you. So once you tell the computer what your model chemistry is, it will calculate all the atomic orbitals for you. It will figure out where they are and what they are. It will then calculate automatically for you all of the molecular orbitals. So it knows how to do a linear combination of atomic orbitals calculation, and it does it for you. And at the end of your run, it'll let you see what your molecular orbitals are. Okay? It should be, and we'll talk about this in one of the later labs, not all atomic orbitals are the same. Some of them are more important than others. So because some atomic orbitals are more important than others, we multiply each AO by a fudge factor, by a constant before the addition happens. So one of the atomic orbitals may get multiplied by a big number like 0.7 because it contributes 70% of the final answer. The other ones might get be multiplied by 0.1 or 10% or 0.05 or 5%. So depending on the relative value of the atomic orbitals, they get multiplied by a constant. And we'll get a little bit into that mathematics later on in some of the other labs. Okay, that's it. So there's 3 approximations. You need to understand Born-Oppenheimer, Hartree-Fock, and LCAO. And that collectively those are called Rotan-Hall. You need to understand that electron cloud, or that probability of finding the electron, is something called a wave function. At least that's a simplistic definition, and we'll get into a little bit more detailed, more sophisticated explanations of these things as we do some of the labs in the next couple weeks. Okay, I want to talk very briefly about units of measure. Some of the units in computational chemistry. You've run into some of these are new. We have a unit in computational chemistry called the Bohr, and it is an atomic unit of length. And I'll leave out A sub O until we do the lab. Okay, and the definition, it's equal to the radius of the first Bohr orbit for a hydrogen atom, and we'll talk about that during this week's lab. Okay, the standard unit of 1 Bohr, it's 5.29 times 10 to the minus 11 meters. Okay, so it's a very, very small unit, needless to say. Okay, and in nanometers, it's 0.0529 nanometers. In picometers, it's 52.9 picometers. And in angstroms, it's 0.529 angstroms. And I hope that you would be able to do all those conversions. My guess is you don't have a lot of experience with nanometers or picometers. You probably have 0 experience with angstroms. But those are the units that we use in computational chemistry, and you'll need to get those into your head. Okay, Hartree you've had some experience with. It's a unit of energy. The textbook definition is that it's equal to twice the energy of the ground state hydrogen atom, and you might get to see that a little bit in this week's lab. Okay, it's equivalent, as many of you have seen, to 627.5 kilocalories per mole. We can also equate it to kilojoules per mole or electron volts per mole. All of these are units of energy. You might have, we've encountered a little bit, but not very much, unit of dipole moment or polarity. It's called a debye. Okay, you've experienced a little bit of bond lengths and bond angles. So bond lengths being measured in usually in units of angstroms, bond angles, of course, being measured in units of degrees. And bond lengths, again, we measure that in angstroms, which is 1 times 10 to the minus 10 meters. Again, a very, very small number. Okay, and that's it. And we'll talk to you about questions later on. Thanks. See ya.